Hello, everyone. Thank you for being here today. This talk today is related to one of my PhD studies. This is a joint work with my supervisors, and Yusri Adesai. This talk is on data-driven methods for constraint customization in optimization models. As you know, there are lots of these days there are lots of optimization-based decision support systems being used in different industries. Most of the time, they are basically based on classical optimization problems in the most common formats. And in many cases, they are being used in companies as a software as a service. It means that the provider of these softwares host the software themselves, and the code base is the same, so they can use the same optimization software in different companies, and they don't need to change it based on different industries. So in this case, in many when they run this optimization software for different industries, in many cases they cannot meet the internal rules and preferences of each industry. So when the input parameters of optimization models are given to the optimization software and the optimal solutions are obtained, in many cases the client, the user, is modifying the optimal solution based on the preferences of the client of themselves, based on the rules of the company, to be able to execute them in the company. If you want to, if a software provider wants to customize the software based on the internal rules of each customer to reflect the reality which is happening in the industry, they need to interview the experts of the company to understand the logic behind the internal rules, so it can be prone to error, and it's very time and cost consuming. And most importantly, it's not possible anymore to have a unified software to be able to run it in different companies. So it's crucial to have a unified data-driven framework to be able to capture the underlying rules that each customer is considering when it is taking the decisions on modifying the optimal solutions obtained by the softwares. The idea here is to combine prescriptive methods with predictive methods to learn these kind of rules as side constraints based on the customer's data, and embed them in an optimization problem. So we assume that for this framework, we assume that we know about the optimization problem, which is considering in the company, and we also assume that the optimization problem has been solved in the company for a period of time. So we have historical data of what is supposed to be what was supposed to be the optimal solution and what happened in the reality. It means that what was the modifications happened in the company. So we can learn from these data and embed the learning model as constraint in the optimization problem. In this case, when the input parameters are given to the optimization models, the software could solve them for each company as a customized optimization model. So the user doesn't need to modify the results anymore, and it can be executed in the company at the first place. So here we see what we will have in the next slide. First, we will talk about the base of the framework, which is base of the work of Hewitt and Fournier. I will explain their framework, and then I will explain what we have done as our contributions to the base paper, and then we will see the performance of the framework on two different problems: knapsack problem and knapsack problem. So, as I said, we assume that we know about the MIP general optimization problem. We call it the GOP here, which is a classic optimization problem. Let's say a knapsack problem in the format of this one you see here. And then we have operational rules as side constraints, in which X is the main decision variable, and V can be added decision variables for, let's say, for example, for scheduling to consider if there are rules or any other kind of rules to be added to the constraints. So by adding these side constraints to the general optimization problem, we will have adapted optimization problem, which is called AOP. We can refer to it as AOP in the next slides. The data-driven framework was introduced in this paper, consists of three main parts, which are shown in blue: learning the models and providing the executable plans by embedding the learning models in the general optimization problem. But since we want to evaluate the performance of the framework, we need to, and we don't have access to real data, we need to generate our data. So at the beginning, we consider our optimization problem, and we generate the parameters of the problem. We need to generate this problem for many decision points, let's say for each day that the optimization problem is being solved. Then we solve the optimization problem to obtain the input features X of the, which are the optimal solutions of the problem, and then we impose the rules to the optimal solutions and create the output features Y. So this is a kind of control setting for data generation, since we know how we want to generate our data. And then we learn from this X and Y as to obtain our side constraints, and then we embed these side constraints in the MILP problem. And for our study, we consider only the methods that are compatible with MILP programming, since we don't want to change the MILP to nonlinear programming. At the end, we solve the adapted problem to obtain the new optimal solutions and validate them with two measures. The first one is computing the percentage of satisfied instances based on the new rules, and the second one is based on the computing the difference between the objective function of AOP and JOP. So with computing, I call it gap. With computing this gap, we see we understand the degradation of the objective function. I will discuss them more in the next slides. Okay. In the study of Hewitt and Fournier, they considered linear regression to learn the side constraint and embed them in the optimization problems. Let's say we have the typical the common optimization problem like this, and then they add they add the regression equations as side constraints. Y is the prediction of executed plans, and we always want this Y to be very close to X. So we add delta as a variable to minimize as a variable, and we want to minimize the differences between X and Y. So we add the total amount of this difference as delta in the objective function. C here is the penalty coefficients to make a balance between these two objective functions. There, like basic objective function we had, and then new objective function. What we want to do is improving this framework by adding regularization to the linear regression and also trying decision trees. And then the study has been done before was only on fractional MILP problems, but we want to validate the framework on some binary problems as well. For regularization, we tested lasso rig and elastic net regression, and the thing is that elastic net is is combining these two, and we want to see the effects of this regularization on the results. But we know that the regularization will not change the regression equations and the embedding process. Also, as I said before, we want to see how we can embed decision trees and in this framework. So we consider here we see the general procedure of how we can embed decision trees in MILP models, but it can I showed the general formats, but it can reduce to when we have only binary tree, like classification tree, or we don't have hyperplane splitting. Here you see we have predictions equations for each leaf node. When we have we define Z as the decision variable for each leaf node to decide about each equation. I forgot to say that this problem is a multi-output problem because we have different decision variables xi, so we have lots of like y of I, and then since it's a multi-output problem, we learn one decision tree. We model one decision tree per each output y. So here we see the prediction equation for each leaf node, and then we have the path to the path of branching the tree. H is the branching coefficient, and G is the branching threshold. And here we see the general format, but when we have a hyperplane splitting, but when we have, for example, only univariate tree, we have only one edge. And in the case of hyperplane splitting, we can have different edge. This equation was added to guarantee choosing one leaf node for each output I, and the other equations are exactly similar to what we had in the linear regression. So let's start with the knapsack problem. When we consider both linear and binary knapsack problem, we have AI as the size of each decision. We want to load different products in a let's say container with the size B, and each product's size is AI, and the profit related to each product is RI. we want to maximize the profit here, and here I showed like some rules to demonstrate how we want to impose these rules on the model. For example, we say we have the same rule for each instance, let's say each day, like x1 has to be less than or equal to 2. And if, for example, we solve our optimization problem and we obtain x1 is not less than x2, let's say x1 is 0.5 and x2 is 0, we need to change the y variable, and x1 and x2 will be both 0, and then we will learn from these changes. Another case can happen when we have different type of rules for different instances for different days. Here I showed how we will impose these rules on the obtain optimal solutions. To generate our data, we considered two sets of two data sets. The first one was a small data set with only 15 variables, and the second one we considered 50 variables. We wanted to see how robust will be the model if we increase the number of variables compared to the number of instances. We consider 80% of the instances for training and 20% of the instances for test. And here we see for linear knapsack problem, we considered 9 sets of rules. The first rule, also the set 4 and set 5, were tested in the previous paper as well. What we wanted to have more different rules, and for example, in step 2, we see we have rules for each decision variable. These graphs here are shown to see the effects of coefficient C on the result of the framework. As you see here, we have we altered the coefficient C from 0 to 500 to see the results. These two are the measures of the validation measures we considered. As you see here, normally with increasing coefficient C, we can increase the satisfaction rate, and it will be stabilized at some point. But the gap will be increased as well. So what we have considered for showing the result is that we increase the C to some extent and chose the best satisfaction rate, and then we reported the related gap. For example, we see when we have set 4, the green line, we have satisfaction of 100% when we have C as 400, and when C is 400, the gap is almost 4%. It shows that by increasing the number of rules, the rate is still 100%. We could obtain 100% satisfaction rate, but the gap is increasing. This is the results for linear knapsack problem. The first column shows that the percentage of the instances which are already satisfied without imposing the learning models. But the rest are the results where we impose the learn model with linear regression, lasso ridge, and regression. As you see here, in most of the cases, adding the learn constraint could increase the satisfaction rate. and the gap are not that much. I mean, the gap is always between 0 and 10%. So it shows that how the framework can increase the satisfaction without affecting the objective function that much. The third column of each method is related to the sparsity of the coefficients of the learned models, and we could figure out that when in ElasticNet and Lasso, when we have more sparsity, we have better results compared to linear and with regression. For the binary knapsack problem, the interesting results were related to when we have classification tree. As you see here, with classification tree, we could almost obtain 100% satisfaction of the model rules when we apply them to the different set of rules. And the point is that the gap is not that much. For example, in the results of Lasso are also promising, but the gap here, we compare the gap of the Lasso and classification tree. We see the gap in classification tree are less than the gap in Lasso. The next problem we considered, which is a more practical problem, is Nernst rostering problem. This problem is a critical problem in healthcare management, and the Nernst rostering problem, they try to assign shifts to nurses where the general objective is to manage the resources where we have less cost. But there are lots of modeling methods for Nernst rostering problem, and we considered one of them as a MILP problem. You see the parameters here. The parameters we consider for the problem here. The decision variable is x, I, j, d when we assign the nurse I to shift j in the date d. We consider this planning horizon p, and then a set of nurses at n, and we consider 3 shifts for this problem. The problem we have here, the objective function is to minimizing the total understaffing and overstaffing. We could have a penalty coefficients alpha and alpha prime to show the effects of understaffing and overstaffing, which one is more important for the hospital. And the basic constraint here is the covering constraints. We want to minimize, as I said, the understaffing and overstaffing. And we also considered 5 other hard constraints for this problem. The most important one, which is always considered in most of the problems, is related to that we don't want to allow a nurse to work more than 1 shift per day. But the others can change in different problems. These are the concerns we assumed from the beginning. But we want also to add some other side constraints to the problem. For data generation, we considered 200 initial planning periods, and We also consider two scenarios when we have a weight, more weight for understaffing, and when we consider the same weight for understaffing and overstaffing. These are the three set of rules we considered for the as a side constraint for this problem. For example, the first one is saying that after a night shift on, the next morning shift has to be off. And as you see here, this is the how we add this kind of constraint to the optimization problem. To evaluate this, evaluate the results of this problem, we considered not only the first gap that we considered for the knapsack problem, we also added three other types of gap. You see the first one, I didn't show it in the knapsack problem, but you see this one is saying that what will be the differences between objective functions when we have the adaptive optimization problem with the learn constraint, and when we don't have the learn constraint and we know the constraint from beforehand, and we solve the optimization problem assuming we know the rules. The other ones are for the other gaps. We just wanted to see the differences between the demand we obtain after adding the side constraints and the demand when we suppose that we know the rules beforehand. We tried the framework for different sides of the problems when we have like 6 to 7 nurses and when the horizon of the scheduling is 10 to 12 days. This is the satisfaction for the cases that we the cases without applying the framework, and the demand here is has been shown only to show that to give a sense to we can compare the average demand for each problem with the different gaps we obtained here. As you see here, the satisfaction could be obtained with all the methods. I didn't represent the other methods, even for the other ones, it was the same. The satisfaction are always 100%, but the point is that the gap in linear regression and less ignorant are much more than classification tree, and that's because in regression we had to increase the coefficient C to some extent to be able to obtain this satisfaction. And the other point was that for linear regression we needed to spend much more time to solve the optimization problems. For classification tree, each instance was solved in, let's say, less than 20 seconds, but for linear regression we had to have a time limit for each instance, like 600 seconds of time limit for the for embedding linear regression in the models. So here we see the outperformance of classification tree compared to the regression for this binary problem. And if we want to wrap up the talk, we extended the data-driven framework proposed in the previous paper. We have used regularized linear regression and decision tree, and we could obtain better results. We also evaluate the framework for binary problems for the first time, and we could obtain good results by adding classification tree. Thank you so much.